Now we look at applications of reading measure. The first application is from the definition of the reading measure for theta. We can get some equivalent forms. For example, theta, according to definition, it is this ratio, right? S is the length of the intercepted arc. So here's the theta, that's S, which is the length of this intercepted arc compared with radius. So this ratio will give you the reading measure of theta. With that formula, we can immediately rewrite it. You see, this is the same. If we multiply both sides by radius, then theta times radius equals S. So we simply multiply both sides by radius. You see the intercepted arc length will be equal to radius times theta. So basically, the same formula. We just look at it. So theta equals S over R, which is the same as S equals R times theta. So now with this new look of the formula, we can calculate S, the intercepted arc length. Arc length is equal to radius times theta, but theta has to be in the reading measure. So be aware, because this formula is from the definition of the reading measure of theta. So immediately we have the arc length formula. So whenever you want to do the arc length, just multiply the radius by theta in readings. So let's look at one example. So here is a theta, which is 4 readings. Okay, here is a theta which measures measuring 4 readings. 4 readings. What's the radius? Radius is 5 inches. So then 4 times 5. See, the 5 is the radius times the theta in readings. So we get a total of 20 inches. That's the corresponding arc length. So this arc length intercepted by theta will be this product, 5 times 4, 20 inches. So finding arc length is to use this formula. So let's look at another example. And here's another example. We have a circle. This circle has a radius of 12 inches. Please find the length of an arc intercepted by a central angle measuring 150 degrees. So if you want to apply the formula immediately, you can use radius times theta. And if you use the 12 inches times the theta, which is 150 degrees, can we do that? Can we calculate arc length this way? Answer is no, because theta is in degrees. So we have to be careful in this formula. When you apply this formula, theta should be in readings. So yes, let's first of all convert this theta into readings before we use the formula. So 150 degrees, when we convert it into readings, we need to multiply the degree measure by pi over 180. So when you multiply, you see you can cancel some common factors, right? Divide by 30, 150 divided by 30 So yeah, it's a 5 pi over 6. So, and that's the reading measure for 150 degrees. So with that reading measure, then we can apply the formula. So the arc length corresponding to 150 degrees, right, will be the radius, which is 12 inches, times the theta in radians, and that's the arc length. So the product, and to get this product, we can cancel the 6 with 12. So that's 2. 2 times 5 is 10, 10 pi. So 10 pi is the arc length. But if you want to get the number, so it's 10, approximately 10 times 3.14. So 10 multiply 3.14, so it's approximately 31.4 inches. That's the arc length. So just be careful when we apply this formula, S equals R theta, theta is in radians. Now, next application is the linear speed and angular speed. Let me show you a picture. So this, on this picture, you see the two concentric circles. So the center is O, is labeled as O. Imagine you have a disk. You have a disk, and suppose we just draw the center of the disk and label it as O. And then we draw two concentric circles on the disk. And you can see there's an inner circle and outer circle. And on the outer circle, we pick a point and call it P. And we link the center and the P. And then we get this radius of outer circle, and the intersection, there's a P prime. That's the radius. OP prime will be the radius of inner circle. So you see P prime is a point on this line segment. But as you can imagine, if the disk revolves around the center, and P will travel a greater distance at per unit time. So that means if we look at the speed, right? So the P, because it's located at the outer circle, so it will travel a greater distance per unit time. So because this segment, right, is going to be at another location. For example, that's the segment. It will be here. So P at certain, and the P prime will be here. So we can know the speed if we're using the distance of the arc length traveled by P will be longer, will be larger than the arc length traveled by P prime. So here's the definition of the linear speed. Linear speed, we denote it by V. V is the arc length traced by a point over this amount of time t. So if we do a ratio, that means the arc length traveled per unit time. So suppose in 2 minutes, traveled by 12 inches, right? Then per minute will be 6 inches. So it's just to make sense with this formula. So S over T is, so the total time is T. If during this time period, it traveled this long, that's the arc length, then per unit time will be this ratio. So that's how we calculate linear speed. And angular speed. Angular speed, we need to just replace, in this formula, we use a different letter for angular speed. So as you can see, the omega for the angular speed, it is defined, definition is different. If we compare the linear speed and angular speed is defined by a different ratio. That is the amount of angle, right, traced or covered by that line segment, and in this time. And if you do the ratio, that is the angle covered per unit time. So that's the angular speed. So let's look at a picture. So this picture, if we want to calculate the linear speed, suppose the initial point is here, and after certain time it traveled to this spot P, then the linear speed will be the total distance traveled, which is the arc length. That divided by the amount of time used to travel that long. So that's the linear speed, the distance over time, right? That's the linear speed. But angular speed will be denoted by omega. So the angle covered during this time period. So that is the theta. Theta over t, that means per unit time, right? This is the total time is t. If you, in this amount of time, if the angle covered is theta, then per unit time will be theta over t, that ratio. So this is the angular speed. So now with the two definitions, and we can calculate linear speed and angular speed as long as we know this information. And also, we can discover that actually linear speed and angular speed are related. What is the relationship? Let's recall that S, the arc length, S, remember if we know the radius, it's by arc length formula, we replace it as radius times theta in radians. So, and the numerator becomes r theta. And denominator, let's keep it as is. It is still t. But then we notice that theta over t, this part is simply angular speed, right? That part is omega. So we can write the linear speed, which is v, which is r times omega. So I just simply put this part is omega. So from here, we see the linear speed v and the angular speed omega are related. That's how they are related. Linear speed v is equal to angular speed omega times radius. Yeah, so we discovered the relationship just from here's how we define linear speed and how we define angular speed, then discover that by definition, these two are related. Yeah, so this is just a quick summary to see that this is a linear speed. And if we replace the arc length S, this S is the same as radius times theta in radians. And then immediately we continue and recognize this is omega. So R times omega is equal to V. So linear speed is angular speed times radius. Now, once we know these several formulas, right? Formula for linear speed, formula for angular speed, and the formula that relates linear and angular speeds. Let's look at one problem. This one problem, just to try to apply the formulas we learned now and then to get, okay, find arc length and linear speed. So here is the question. So the question says, if we have a clock, the minute hand of a clock is 6 inches long and moves from 3 to 7. Round your answers. So what we're trying to do is, yeah, doesn't A and B to the nearest hundreds. Yeah, so find the arc length traced by the tip of the minute hand. So the first question, so you just try to imagine this clock. This one, the clock, right? It's a circle. Let's draw a circle. And then you suppose this minute hand of a clock is 6 inches long. So let's just imagine this hand is moving. So this hand is like a circle of radius 6 inches long, and it's going to move from 3, right? So this is 12 o'clock. This is 1, 2, 3. Yeah. And this is 3 o'clock. If from 3 to 7, let's quickly first get 6. Here's the 6 and 7. So from 3 to 7. Okay, so now how many radians is this? So I can see this is the starting and this is the ending. And this is the angle from 3 to 7. So if we want to find the arc length traced by the minute hand, so that is the arc length, the starting from this point, the arc length, right? We can use a bright color to show that arc length is actually this portion. Yeah, so that's the portion traced by the minute hand from 3 to 7. So how long is that? It's the arc length formula. So S equals radius times theta. But remember, theta is in radians. So radius is 6 because that's the length of the minute hand. That's the radius. And theta in angle, this theta here. So what is the theta in radians? Oh, we see that how many 30 degree, right? So this from, because a complete rotation is 360 and we divide into 12 portions. So each part is 30 degree. 30 degrees. So we have four of, so this one is 30, 30, 30, 30. So we have four of the 30 degrees. So it's actually 120 degrees. So this angle traced is 120. But we don't want to use the 120 degree measure. We want to use the reading measure. Remember, reading measure, you have to divide 180 and multiply it by pi. This is how we convert it into reading measure. So this 120 degree here, this angle in reading will be, yeah, after we multiply these two, we can get pi and cancel. Yeah, we can cancel 3. And still you have a common factor. So you can cancel a 2. Cancel a 2. So it's a 2 pi over 3, right? 2/3 pi. Okay. So 2/3 pi in for the theta. Now we're using this formula correctly because radius times theta in radians. So, and then final answer will be, okay, so if we see that 3 and 6 can, yeah, it's basically 6 over 3 is 2, right? Twice of 2 pi is 4 pi. So this arc length traveled by the tip of the minute hand, this right portion, is just 4 pi. 4 pi, what is the unit? In inches, right? We can put 4 pi inches. Yeah, of course, if you want to know exact number value, then you can use 3.14 to get approximate inch. So that is 3.14 times 4 pi, right? So that is how many inches. So after we get that, find the linear speed of the tip of the minute hand. So if you know how the distance traveled by the minute hand, then how long it takes from 3 to 7, that's 4 minutes, right? So then, so after we get the total arc length traced by the tip of the minute hand, and the linear speed will be that distance divided by 4 minutes. So each minute will be pi. Yeah, because of 4 pi over 4, in 4 minutes, it traveled 4 pi inches, right? So each unit of time, that means per minute, it travels just a pi inches per minute, which is 3.14, approximately 3.14 inches per minute. So we use this formula for linear speed to calculate how many inches this tape of the minute hand travels per unit time. And let's try another one. So this problem, you want to find angular speed. So there is an outdoor windmill spinner, has a radius of 5 feet, it revolves. So 5 feet is the radius. Let's draw this 5 feet, and revolves at 6 revolutions per second. 6 revolutions. So if you do one revolution, one complete revolution, that is 2 pi radians, right? If 6 complete revolution, that will be how many radians? So 2 pi times 6, 12 pi radians. Per second. Yeah. So each second, that's the amount of angles in radians that it will cover. So let's try to answer the A and B. Find the angular speed of the spinner in radians per second. Oh, we just got that one. Yeah, that is the angle in radians per second. So 12 pi radians. So that's the angular speed. And what's the linear speed of the tips of the blades? So if we know the angular speed omega, then the tip, you see, if it is doing the 6 complete, yeah, it revolves at 6 revolutions around the center, right, per second. So that means the linear speed using by the formula, it's a radius times omega. If we know the omega, which is 12 pi radians per second, that's the angular speed times radius. Do we know radius? Radius is 5. Yes, 5 times angular speed. And this will give 60 pi. 60 pi, the unit is the feet. Yeah, the radius is 5 feet. So feet per second. Yeah, so this is the 60 pi feet per second for the linear speed and 12 pi radians per second as angular speed. And one more application. So if we have a circle of radius r, and we want to know area of this sector, just this portion, how can I calculate area of the sector with the central angle theta? So let's think of the entire circle. Entire circle, we know the area formula. It's simply pi r squared. But this sector in pink is only portion of the entire area, right? The entire circle, it has the area pi r squared. So what percent? So this is, we use the angle, this portion corresponding to this sector, this central angle, the complete rotation 2 pi. So suppose theta is in radians over the 2 pi, the complete the circle corresponding to the central angle of 2 pi. So this theta compared to 2 pi is only, that shows the percent of this, the area of the sector compared to the whole, the area of the whole circle. So that is the percent of the whole circle area. Multiply this two, what do I get? What do we get? So let's see if when we multiply, we can see the pi is canceled and just the half of the theta and radius squared. So that's the area formula for the sector. area for sector, if we see this part is the area of the whole circle, and this is the percent, this percent of the whole circle, right? Because the sector has the corresponds to the central angle measuring in theta radians. 2 pi is the whole circle. Yeah, so if with the whole circle, then the theta is yeah, compared to whole circle, that's the percent. So this sector takes only this percent of the whole area, which is pi r square. So after we cancel the pi, we can see half of theta r square as the area formula for the sector. So be aware that theta is also in radians. So when we use this formula, this is the, you see theta in radians compare with the complete, the center angle also in radians. So theta has to be in radians for when we derived this formula. Okay, so now let's use this formula. So if you know all this information, you can find area of a sector, such as a circle with radius being 9 inches. 9 inches. So the radius is 9 inches. And the central angle measuring 60 degrees. But we use the area formula for the sector. So we want to find area of the sector with central angle being 60 degree. So the area will be half central angle has to be in radians. So the 60 degree is not yet in radians. We have to convert it. Theta r squared. So r squared. So we know that radius. So half and 60 radians, and once you convert it into degree, 60 degrees into radians will be pi over 3. That's the radians. So radius is 9 squared. So now that's the formula. We're applying the formula for the to calculate area of the sector. So now you see this is 9 squared is 81 times pi over 6. But actually we notice that 3 can be canceled, right? So there's a common factor. 3, we cancel 3. Divide 3 here, divide 3. 27 pi over 2. So the final answer will be 27 pi over 2. That's the area in square inches of the sector corresponding to the central angle. So if you want, you can write approximately, that is 27 times 3.14 over 2, which is approximately 42.39 square inches.